Taking command as a ship's master transforms navigation from the act of following a route into the management of a total risk profile. This role moves beyond the bridge's digital track lines to own the vessel's survival against the physical extremes of the sea. The master must maintain the vessel within a narrow corridor of safety, navigating rigid statutory boundaries while simultaneously managing the unpredictable kinetic energy of the marine environment. Highly integrated electronic bridges create the risk of single-point failures. A localized spoofing event, where false GNSS signals are broadcast to override legitimate data, or a high-latitude satellite blackout, can instantly blind the ship's primary sensors. Advanced shipboard management requires absolute command over 3 distinct domains to counter these failures: positional verification, hazard management, and empirical ship handling. These domains interact to create a fail-safe passage plan. Each pillar provides a layer of redundancy, ensuring that no single sensor failure results in a grounding or collision. Synthesizing this interconnected matrix allows a master to mathematically and practically guarantee a safe transit, even when automated systems are completely lost. This chart shows how modern navigation derives instantaneous vessel speed using the Doppler shift of satellite carrier frequencies. As the ship moves relative to the orbiting satellite, the receiver tracks how the carrier frequency waveform compresses or expands to calculate velocity. These systems remain vulnerable. High-latitude orbits degrade the accuracy of satellite geometry, and unencrypted signals are susceptible to spoofing, feeding a false position to the EDIS, the electronic chart display and information system, without triggering a system alarm. When digital positional integrity is compromised, the master relies on the primary analog fallback, star sights. The process begins by calculating the local hour angle, or LHA, of Aries from the Nautical Almanac. This value defines the position of the celestial reference meridian relative to the ship's dead reckoning longitude at the exact moment of observation. This starfinder pre-calculates a star's altitude and azimuth. At point A, the 180-360 line aligns with the North Pole. At point B, aligning the center crosshair with the ship's latitude reveals exact altitude and bearing data for visible stars on the horizon. This diagram illustrates the intercept method. By taking 3 sights in quick succession, the master plots azimuths from a single dead reckoning position. The intersection of these 3 position lines creates a highly accurate fix, independent of any electronic input. These observations must occur within strict X-meridian limits. These are precise time windows, often less than 30 minutes, during which a celestial body's altitude change is predictable enough for accurate latitude calculations. Maintaining these analog skills transforms a potential total system failure into a manageable navigational challenge, ensuring the ship is never truly lost. While celestial fixes secure the open ocean, coastal navigation requires managing the complexities of traffic separation schemes and submerged hazards. Under SOLAS Regulation V/10, the use of mandatory ships routing systems is a legal requirement. These schemes are designed to inhibit collisions in areas of high traffic density or restricted sea room. This table details the Ayala lateral marks for Region A. In this system, used across Europe and most of Asia, red cylindrical buoys mark the port side of the channel, while green conical buoys mark the starboard side. In Region B, which includes the Americas and Japan, these colors are entirely reversed. A master must anticipate this shift in the visual vocabulary of the sea to maintain the correct side of the channel. For hazards located outside of defined channels, the master looks for cardinal marks. These buoys indicate the direction of the deepest water relative to the hazard, using distinct top marks, such as 2 cones pointing toward each other for a west mark. This chart shows a clearing bearing, establishing a geometric safety corridor using a fixed landmark.
Here, a safe zone lies between true bearings of 265 and 275 degrees. As long as the lighthouse's bearing remains within these limits, the vessel is mathematically protected. When no fixed object is available, the master employs clearing marks, lining up 2 distinct visual features, like an island and a buoy. If the 2 objects remain open, with a visible gap between them, the ship is clear of the danger. Mastering this geometry allows the master to construct a mathematically enforced fortress around the vessel, protecting the hull in highly restricted coastal waters. Navigating the poles introduces hazards that exceed standard coastal risks. Ice-infested waters require specialized hull designs and strict adherence to the Polar Code. The Polar Code classifies ships into 3 categories: Category A for medium first-year ice, Category B for thin first-year ice, and Category C for open water. These ratings dictate exactly where and when a vessel can legally operate. The most significant physical threat here is ice accretion. High winds and sub-zero temperatures cause sea spray to freeze instantly upon contact with the ship's superstructure. This accumulated ice adds massive weight high above the waterline, which raises the ship's center of gravity. This results in a dangerous, immediate reduction in the ship's stability. As the ice thickens, total displacement increases, while freeboard and buoyancy decrease. If the ice is not physically removed, the vessel risks a catastrophic loss of stability and capsize. Digital hazards also increase. The poles are located in Sea Area A4, outside the range of geostationary communication satellites. Ships must rely on high-frequency radio and polar orbiting emergency systems. Standard navigational tools degrade as well. The extreme magnetic dip near the poles, where the Earth's magnetic field lines point vertically, renders traditional magnetic compasses unreliable. Surviving these operations requires the master to integrate the structural limits of their ice class with the anticipated failure of standard communication and navigation suites. The final pillar is the command of the ship's physical mass. A master must know exactly how hundreds of thousands of tons will respond to helm orders before they are issued. The bridge displays a wheelhouse poster with general data, but for critical maneuvers, the master relies on the maneuvering booklet. This contains highly detailed empirical data derived from the ship's original sea trials. Engineers determine a ship's steering characteristics through the yaw test. This procedure measures the vessel's directional stability and responsiveness to its rudder. This graph maps a zigzag test. Once the heading changes 10 degrees, rudder is immediately reversed. The graph tracks the first overshoot angle, excess heading reached after counter rudder, measuring the hull's momentum. A second overshoot angle is measured on the return swing. Smaller overshoot angles always indicate superior controllability. The master uses this data to predict the ship's physics during high-stakes maneuvers, such as crash stops or tight channel transits. Commanding this empirical data allows the master to eliminate guesswork, replacing it with the precise prediction of the vessel's physical behavior. Safe command is the simultaneous execution of all 3 pillars: positional verification, hazard management, and empirical ship handling. A passage plan functions as a continuous equilibrium between external environmental hazards and the documented physical limits of the hull. The charted trackline acts as a starting point for this ongoing mathematical assessment. Absolute safety requires maintaining analog fallbacks, from celestial mechanics to the mastery of heavy weather physics, ensuring the ship is protected regardless of system status. The core of the master's capability lies in the ability to synthesize these complex, overlapping data streams into a single, cohesive operational decision. By commanding this navigational triad, the master removes luck from the equation, mathematically guaranteeing the safety of the crew, the cargo, and the vessel against the extremes of the sea.